Okay, welcome back to Phase Transformations. Today I want to talk specifically about the representative diagrams that indicate and show these different phase changes for steel. Now, what we're going to look at, as I told you, each one of these IT diagrams has its own unique, or each alloy has its own unique diagram. Now, this is going to be for a eutectoid steel, which means roughly we're talking about, a steel with carbon about 0.8% carbon, which is the eutectoid. Now, uh, we looked at this diagram last day, but just a review here. This is the actual region in here that concerns us as far as what we need, what kind of products we're going to be getting. And this P, of course, stands for perlite, and this B stands for bainite. So this is perlite and bainite, and of course down here is martensite. Martensite. All right. So what I'm going to do is show you some curves, some potential cooling curves here, and what possibly can happen. Now the other thing, of course, this is showing temperature in degrees Fahrenheit, and this is showing temperature in degrees Celsius. But also, as I showed you last day, very easily there on this side of the scale, which are more likely to be temperature over here, and then on this side of the scale, it usually will be a Rockwell C-scale hardness values all up and down here vertically. So just remember that that's very much a possibility, because that will tell you what you're going to get once you do these different heat treating processes. So, all right, and we know that this little point, this little apex, is called the nose, the pyrolytic nose, and we know that we can move that nose left and right based on the different alloy content, and it's highly subjected to the alloy content. The more carbon content you have, the more this nose moves to the right. The more the big three alloying elements that we'll talk about later on, like manganese, molybdenum, and chromium, those three also have a tendency to move this nose to the right, which then opens up this gap and allows for more opportunity to obtain martensitic structure, if in fact has the right composition, which we're going to talk about some factors of how you go about getting martensite to begin with that affect that. But I wanted to show you some potential cooling rate curves here to see what might happen. Now, the first ones are kind of obvious, and obviously you would start. All of them are going to have to start up here, all right, and because we have to transform that steel into austenite, which is an FCC structure. So they're all going to be, and since this is eutectoid, we know its eutectoid temperature is 1333, so plus 50 degrees, roughly 1350 or 88, something like that, would work. So we're talking about up here starting. Now, if we decided we're just going to do this, and again the three quenching mediums are, of course, in order of severity would be brine, and then water, and then oil. Okay, so let's say we just weren't trying to do much and we're just going to do it in oil. We might have something that looks very similar to this, just something that looks like that. And of course, this being the start of transformation line, this is the start, this is the finish line of the transformation. And on here is transformations that are taking place. And so you can see here that this enters at perlite. I'm just going to dash the line here showing the transformation, and then exits perlite. And actually it may enter kind of like almost coarse perlite, enter fine perlite, but really that's not that necessary to know the difference right now. So you can see out of that resulting, and see it started here at about 5 seconds or so, and ended up maybe 15 seconds to go from start to finish, but it's 100%. So this would be a 100% perlite structure. All right. Okay, now the other thing we can do, of course, if you decided to use a brine, we could get a curve that probably could look something like this. All right. And notice that this never goes into this region, so it bypassed everything. And so it has a start here, Martensite start, and then it just keeps going and finishes at Martensite. So it took about maybe 20 seconds to get there, and then about 100 seconds or so, a little over a minute or so to finish off. So, but it's 100. This would be a 100% Martensite structure. A 100% Martensite structure. Okay. Now, so here's some things. These are constant cooling rates. I mean, they all kind of have the same slope to them, and that takes place all the time. But here's something that could possibly happen. We could take, if we wanted to, you say, well, how we go about getting a 100% Bainite structure, which is intermediate as far as its strength and hardness goes. You could do something like this. You could quench this fairly rapidly, and this comes to experience, of course, for how long and what quenching media. But then you could put it immediately in a salt bath, and what a salt bath does, it's molten salt, and it maintains a specific temperature, and so it would maintain this potential specific temperature. Let's say we want to get it around 900, let's say. So you'd bring this down here to about 900. You take it out of the quenching media, put it in this salt bath, and then that kind of levels it off. And so you can see now that this structure enters Bainite right here at about 5 seconds, 3 seconds. All right. And then it goes into the salt bath where it holds that temperature constant at this little less than 900 degrees and finishes off and finishes in Bainite. So this curve right here, this would be a 100% Bainite alloy. All right. So that's something you could do. Then there's possibilities of something like this too. You can get mixtures. You can get hybrids. Let's say you took something like, let's say, let me get something we got green that works. Let's say you came down here and you had a cooling rate, and it went something like this, where it came down and it entered perlite like this. Something like that. All right, based upon one of these quenching media here. Notice that it went in right here in perlite at a certain time, and it got to the maximum, and this is a 50% line. This dotted line is a 50% line. It got to 50% perlite. That was its maximum, but it kept falling off. Well, it exited down here, technically in the Bainite region, but that is a starting or a beginning transformation line, so that did not affect it. So what this would represent would be an alloy. Its maximum content of perlite was at 50%. So this would be a 50% perlite, and the rest of it didn't go anything else except the rest of whatever was left over, that unstable austenite, whatever was left over, would turn into martensite. So it would be a 50% martensite alloy. Okay, so those are the possibilities. There are lots of different types and things as far as what could happen with this thing. But just so you understand the basics of how these cooling trajectory curves work, and these are all predicated on the type of quenching media that takes place. All right. So let me show you some factors here that, and let me make this a little bit larger screen now. Hold on. Okay. So now let's look at three factors that affect Martensite, structure transformation. Okay, so these aren't in any particular order, but the first thing obviously is going to be the composition of the alloy. If you do not have enough carbon and or the alloying elements in there, you'll never have a shot at getting there because the nose will be too far over. All right, the nose would be too far over. For instance, just abbreviated thing. You could have a diagram something like this. Okay, where this nose is so close, it's almost impossible to go through here and not get one of these products, if not all of them, because the time would be so small here. So again, that affects the composition. That affects whether or not you can get martensitic structure, either part or full martensitic formation or transformation. Okay. So the other thing, and of course, if you add those elements, then what happens is you get a curve that looks something like this, something like that. All right, so now this is a big distance between here and here. So that's because we added a lot of those more carbon and other alloying elements. So that widens that gap and enhances the opportunity to get down here into martensite without going into one of these other microconstituents. And these are all microconstituents, by the way. The perlite, the bainite, the martensite, those are all microconstituents. They're very visible on a microscope. You can see what they look like. You can definitely tell which one's which. All right, so that's the other one. And the other one is the type, as I mentioned before, the type of quenching media affects it. All right, obviously. You're not going to get there if you try to get 100% martensite and you're using oil or something. Let's say, probably not going to work. And then the other one is obvious, is the size and shape of part. That's going to affect how much martensite might be transformed. Okay, because if you have a part that's really thick and then has thin sections, that's going to be difficult. So those are some things to be aware of as far as factors that affect martensitic structure transformation. Okay. Now, let's see. I wanted to talk just briefly about martensite itself. Okay. And the video is about to end, so I'm going to run out of time. But just understand that martensite, I'll start off this way, is the basis for all hardened carbon steel. All right, is the basis for all hardened carbon steel. Now, it is something you need to understand also is that martensite, this microconstituent, is only formed. It's a diffusionless process. It's a diffusionless process when it goes from, and there goes the timer, when it goes from gamma iron, aka austenite, which is an FCC, when it transforms into Martensite, it's more of a shearing process. It's what I call atomic bedlam. I mean, this stuff goes, it just instantaneously changes over, and so it doesn't have time to slowly diffuse out like it does in the phase diagrams. And so therefore, in order to retain all of the carbon that's in the austenitic structure in that FCC, it transforms into a body-centered tetragonal, crystalline structure. But it maintains that carbon. So it really shears, and I could draw you a picture of how that works. If you put 3 or 4 FCC lattices together, and I could show you where those are, and then shearing across, you come up with a body-centered tetragonal, which still, interstitially speaking, would hold the same amount of carbon. So you maintain that, but this martensite is a room temperature stable microconstituent, all right, solid phase. So that's what's taking place here. It's a diffusionless process. It forms a body-centered tetragonal from an FCC austenite, okay? And it is very, very, very hard, as we said before, very hard and brittle. And the only way we can use it, it has to go back and be something we called tempered, which means we put it back in a furnace, but not the heat treating furnace to austenitize it. We put it in a furnace, maybe depending upon the alloy, but usually somewhere around 350 to maybe up to as high as 500 degrees Fahrenheit, and let it soak for a particular period of time. That reintroduces some of those properties that were lost when it became so hard and so strong, like most of the top properties associated with toughness and ductility start to go back into that product. But still, it will maintain a good amount of strength and hardness, but it now becomes very usable. All right, so I'm going to have to stop there, and well, actually, real quickly, I think I can get this in. This is what the possible transformations are. Let me blow that up for you right quick. All right, these are the possible transformations that can take place. Real quickly, you can see here from austenite, if you do a slow cool, you're going to end up with pearlite. All right, and with obviously pearlite with these different proeutectoid phases potentially. If you do a moderate cool, you can come up with a bainite, and that's a much more strong, better properties than pearlite. If you do a rapid quench, you're going to come up with this again, body-centered tetragonal martensite, which again, as I said, is a diffusionless process. Now, here is, and then of course you have to reheat it, and what I said, temper it. Okay. Now here's something realize real quickly. These are the general trends. Starting with spherodite, which is that really, really soft material where you just soak it just below its A1 line for a great period of time. It becomes very, very soft, very, very ductile, very, very fabric capable, very, very machinable. But if you go from here, coarse pearlite, fine pearlite, bainite, tempered martensite, and martensite, as you go up, strength is increasing, okay? But on the other side, martensite has no ductility, so ductility increases as we go down, or in other words, there's more ductility here than obviously up here. All right, so that shows the general trends of what's taking place between the properties of strength and the properties of ductility as you transform into these different microconstituent products that are representative in these isothermal transformation diagrams. So we will move on to alloys and heat treating next video.